All right, so let's talk about transformations of functions. We've gone over this information and we've been graphing functions all semester, but we've kind of been graphing transformations of functions without me giving any justification for why we graph transformations of functions the way that we do. So what I want to go through today is kind of just the logic behind why functions get transformed the way that they do. So just as kind of a warm-up, right? So remember we have this square root function. Let's just graph this thing to remind us how this goes. So when you have an x minus 3 like this means you're going to be going right 3 units. And when you have a negative 2 on the outside there, then that means you're going to go down 2. And so if you have a basic understanding of what g of x equals square root x looks like, then you can graph this function by just taking this one and shifting it right 3 and down 2. This one usually goes through 0, 0, but we're going to be going right 3 and down 2. So usually the way that I have been doing this is just to shift the axes, right 3 and down 2. And now you can think of this as your new axis system, and then you're going to graph g of x with respect to this axis system. So it goes through 0, 0, 1, 1, 3, 4, 2, and ends up looking something like that. So that's easy enough. But what if we had something more complicated like this, right? This would be a beast to try to graph. So we're going to look at these things in a little bit more detail so that we can handle these kinds of situations. So here's how transformations work. So let f be a function. A linear transformation of f is a composition of f with a linear function. The composition could be on the inside or on the outside or both. So for example, let f be a function and let h of x be rx plus s. A linear transformation of f would be either h of f or f of h, right? H of f would be r times f of x plus s. F of h would be f of rx plus s. In case 1, the transformation h is the outer function. And when you have a transformation that's the outer function, it's easy to see what happens to an arbitrary point AB, right? So if AB is on f, then f of a equals b. And therefore, r times f of a plus s is just r times b plus s. So the point a, rb plus s, is on the graph of r times f of x plus s. So putting it all together, right, if ab is on f, then a times rb plus s is on r f of x plus s. So in other words, when you're applying when the transformation that you're applying is the outer function, right? So when these transformations are taking place outside, so when they're not what you're plugging into the function, but they're stuff that you're doing to the function value afterwards, right? When it's being done on the outside of the function, then nothing happens to the x coordinate, right? A, b, and then a, rb plus s, right? So nothing happens to the x coordinate. But what we do is we apply the transformations to the y coordinate, right? So we multiply the y coordinate by r and then add s to it. So that's when your transformation is the outer function. When the transformation is the inner function, things get a little bit more complicated. Okay? So note that if h is the inner function and if ab is on f, that does not, so ab on f would imply that f of a equals b, but that doesn't mean f of ra plus s equals b, right? So so instead, what we have to do is we have to find x so that f of x equals b. So in other words, we're going to solve a equals rx plus s for x, right? Rx plus s is the transformation that's being applied, and so we solve this thing for x. So to do that, we would subtract s and then divide by r. We would get a minus s over r. So x is a minus s over r. So if AB is on F, then f of A equals B. And when x equals A minus S over R, we would get this, right? F of Rx plus S would be f of R times X, A minus S over R, plus S. The R's would cancel, then the S's would cancel, and you would be left with f of A. And f of A equals B. We know that f of A equals B, right? So, putting it all together, if AB is on F, then A minus S over RB is on f of Rx plus S. So when the transformation is the inner function, nothing happens to the y-coordinate, right? So note that the y-coordinate remains the same. But what does happen is that we apply not the transformation, but the opposite of the transformation to the x-coordinate, right? So on the inside, we're multiplying by r and then adding s. But the way that we actually end up applying that transformation is we subtract s and then divide by r. So we apply the opposite of the stated operation in the opposite order of operations, and this is the reason for that. Okay. So in summary, if we're trying to apply a transformation and the outer function, and we have a transformation on the outer function, then that's going to manipulate the y-coordinate. We're going to perform the given operations to the y-coordinate using the correct order of operations. But if the transformation is the inner function, that's going to manipulate the x-coordinate, and to do that we perform the opposite of the given operations to the x-coordinate using reverse order of operations. So there are a couple of ways that you might think about this. One way that you could think about it is just to take the point and apply the transformations. Another thing you could do would be to set the x-coordinate equal to the inner function and then solve for x, right? And then once you've done that, you can plug that value in to the function to figure out what the y value is. So I'll show you both methods with an example. So let's say that f of x equals square root of x. The following points are on the graph of f. Find the corresponding points on the graph of g of x equals negative 2 times the square root of 5x minus 1 plus 7, which is a pretty nasty function, right? So we know that 1, 1 is on the graph of f. The question is, what's the corresponding point on the graph of g? Well, one way to find that, so here's, first method. One way to find that would be to say, well, I'm going to take the point 1, 1, and I'm going to apply the transformations that I see here. So what I see here, first of all, for the inner function, I have a 5x minus 1. That's going to manipulate the x-coordinate, but it's going to manipulate it in a way that I do the opposite of what I see in the opposite order of operations. So instead of multiplying my x-coordinate by 5 and then subtracting 1, I'm actually going to add 1 to my x-coordinate and then divide by 5. It's kind of weird. But I'm going to add 1 to my x-coordinate, then I'm going to divide by 5. That takes care of the transformation on the inside. Now the transformations on the outside of the function, the negative 2 and the 7, those affect the y-coordinate, and I don't do the opposite of what I see, I do exactly what's written. So I'm going to multiply the y-coordinate by negative 2, and then I'm going to add 7. So I multiply the y-coordinate by negative 2, and then I add 7. Okay, so the point 1, 1 is on the graph of f. The corresponding point on the graph of g is the point 2/5, 5. Okay, that's how that transformation works. So there's one way of doing it, and you can keep track of what we did, right? We added 1 to x, and then we divided x by 2. Here we multiplied y times negative 2, and then we divided y, or then we added 7 to y, right? So you can kind of keep track of each of the transformations. Here's another way to do the same thing. So another way to do the same thing is to take the x-coordinate, 1, and set it equal to the inner function, 5x minus 1. So we're going to say 5x minus 1 equals 1, and then you solve for x, right? You solve for x. So I would add 1, and then divide by 5. You get x equals 2/5. So the x-coordinate of my point on G is going to be 2/5. If I want to find the y coordinate, well then I just plug that in, right? I find G of 2/5. That's going to be negative 2 times the square root of 5 times 2/5 minus 1 plus 7. So that's negative 2 times the square root of 2 minus 1. This is negative 2 times the square root of 1. Right? The inside stuff became 1. We engineered it that way, right? We engineered it that way. Square root of 1 is 1. 1 times negative 2 is negative 2. Negative 2 plus 7 is 5. So there you go, right? We get the same ordered pair, 2/5, comma 5. So you're welcome to do this in any way that you find easiest, any way you like. I might stick to the first way. I think it's a little bit, I don't know, it doesn't take as much space on the page to do it. But if you like the second way better, do it the second way. Okay. Part B, 4, 2. This is definitely on the graph of f of x equals square root of x. We want to know what's the corresponding point on g of x equals negative 2 root 5x minus 1 plus 7. Okay, so what's the corresponding point on g of x? Well, we're going to take 4, 2, and first we're going to add 1 to the x coordinate. Then we're going to divide by 5. And that takes care of the inner transformation. Then the outer transformation, we're going to multiply the y coordinate by negative 2. And then we're going to add 7. So if 4, 2 is on f of x equals square root of x, then 1, 3 is on g of x, right? Again, you could do this, so that's one way to do it. You could do it by setting 4 equal to the inner function 5x minus 1, and then solving for x. You get 5 equals 5x, x equals 1, and then you plug that back into g. You say g of 1 is negative 2, square root 5 times 1 minus 1 plus 7. That's negative 2 root 5 minus 1 is 4. Square root of 4 is 2. Negative 4 plus 7 is 3. Right? So you get 1, 3 again. So however you prefer to do it, again, is fine with me. One thing that I will warn you of is that it's very important that we apply the transformations in the correct order, and this is more for those of you who are thinking about doing these things using method 1. If you're using method 2, you don't have to worry about this so much. But if you're using method 1, make sure that you apply the transformations in the correct order. For example, flipping and then shifting is not necessarily the same as shifting and then flipping. So for example, for g of x equals negative 2 times 2x plus 3 squared plus 5, the parent function is just x squared, right? This is just a quadratic. It's a parabola, but some crazy transformations have been done to it. Now we know that on the parabola f of x, 1, 1 is on that graph. The point 1, 1 is on that graph. So we might want to see what point 1, 1 corresponds to on the graph of g. If we apply the transformations in the wrong order, though, we're going to run into trouble. So if we take 1, 1, first we would need to subtract 3 from x, right? 1 minus 3 is negative 2, right? So far, so good. Then we would need to divide by 2. Negative 2 divided by 2 is negative 1. Okay, still good, right? So far, so good. And that takes care of the transformations to x. Now the transformations to y, we're going to multiply y by negative 2. So we should get negative 1, negative 2. But instead we're writing down negative 2, 6. Now why did we get this? I think it's because whoever was doing this did it in the wrong order, and I think they tried to add 5 to the y coordinate before they multiplied by negative 2. In fact, I'm sure that's what they did. 1 plus 5 is 6, and then 6 times negative 2 is negative 12. But that's the wrong order, right? When you're applying the transformations on the outside to your y coordinate, you use correct order of operations. So you would take 1, multiply it by negative 2, and get negative 2, and then add 5, and you'd get 3. So you should end up at 3 over here. This has an additional problem where for some reason we went from negative 1 to negative 2, and I'm not sure why that changed. But this should have been we should have multiplied by -2 first. And then added 5 to end up at -1, 3. Yeah, so the right order would be, 1, 1, goes to -2, 1, goes to -1, 1, goes to -1, -2, goes to -1, 3. That's the correct order. Okay, so just be aware of that, right? Make sure you're getting things in the correct order. When you're applying transformations on the inside, you do the opposite of what you see in the opposite order of operations. When you're applying, you do that to the x-coordinate. When you're applying transformations to the outside, you apply those to the y-coordinate. You do the exact thing that you see in the exact order of operations. Okay. Here's another example of this. So it says, use the graph of f of x below to graph g of x equals -2 times f of x minus 3 plus 1. Here's a great example where we can't do method 2 because we don't even know what f of x is. We're not given what the function is. We're just given that this is what its graph looks like. So if we wanted to graph g of x, we're pretty much going to have to use method 1. And to do it, I'm just going to pick a few important kind of key points to see where they end up. So I think the vertex of this parabola would be a good point. That's the point -3, 2. This point would be a good point to plot, -2, 1. This point would be a good point to plot. And then so would this one. And that might be good enough. I don't know. I might get this point and this point as well, just to make sure that we end up in the right kind of trajectory. So let's see. So starting at the left, right? This is the point -4, 1. -4, 1. Where's -4, 1 going to end up? Well, I'm going to add 3 to the x-coordinate. And then that's all the transformations being applied to the x-coordinate. To the y-coordinate, I'm going to multiply by -2. And then I'm going to add 1. So -4, 1 ends up at -1, -1. Okay, what about -3, 2? And in each of these things, I'm doing the same thing, right? I'm going to add 3 to the x-coordinate. Then I'm going to multiply the y-coordinate by -2. And then I'm going to add 1 to the y-coordinate. So I end up at 0, -3. What about -2, 1? I add 3, multiply by -2, add 1. I end up at 1, -1. Okay, so there's my parabola. Notice that it looks like it's been flipped over, which makes sense because of that negative sign. It's been shifted right a little bit, but not up. It kind of got shifted down. That's because of the reflection, right? It got shifted up, but then reflected, and so it ends up down here. It's also been stretched, right? The vertical distance between these points is just 1, but between these points it's 2, right? So it's been stretched by a factor of 2. So everything's making sense so far. Let's see where 0, 1 ends up. I'm going to add 3, multiply by -2, and add 1. So 3, -1. I'm going to end up off the graph probably. 1, 0. Where does that end up? Add 3, multiply by -2, add 1. So that ends up at 4, 1. And then one more, 2, 1. Where does that end up? So I'm going to add 3, multiply by -2, add 1. So 5, -1. Okay. So I think what I get is something like this. Parabola there, straight line there, then the absolute value thing there. And by the way, this is going to keep going forever. Okay, so hopefully that makes sense to you. Of course, in order to be able to apply a transformation, we need to have a good grasp on what the parent function looks like and what points are on that parent function. And so you should memorize the shapes of the graphs and the standard points for shifting discussed in chapters 2 and 3. Or, alternatively, take a look at the chart in the introduction to this chapter. If you didn't watch that video, make sure you watch it and fill in the blanks in that chart on the introduction to the chapter. Because it has all of the shapes of the graphs along with the standard points that I want you to transform. So let's practice doing some of these things from memory. So we have -2 times absolute value of negative x plus 3 plus 3. Well, I know that on f of x, maybe I'll call it g of x equals absolute value of x. I know that on this graph, the points 0, 0, 1, 1, and -1, 1 are the ones that I want to be able to plot, because that'll give me my vertex, and then it'll also tell me kind of how stretched out the graph is. So for this function, first I'm going to subtract 3 from the x coordinate, and then I'm going to multiply the x coordinate by, or divide, I guess, by -1. And then for the outer function, I'm going to multiply by -2, -2y, and then I'm going to add 3. So the vertex ends up at 3, 3. Right? That's maybe a little bit surprising because you might think, well, it's plus. Shouldn't it end up at -3, 3? But because of this negative sign here, that kind of messes this thing up. It's like if you factor out the negative, then this becomes a -3, so you end up at, your vertex ends up at 3, 3, sure enough. 1, 1. Subtract 3. Multiply by -1. Multiply by -2. Oh, and then what did I do? I added 3, right? So plus 3, you end up at 2, 1. 2, 1. Is that right? Hold on a second. 1, 1. Subtract 3, multiply by -1. Multiply by -2. Yeah. And then add 3. Yep, so you end up at 2, 1. Something's not lining up about this because, oh, that's because that's 2, 2. 2, 1 is right there. Okay. I was going to say there needs to be a vertical stretch by a factor of 2. Well, there it is, right? I was just plotting the point wrong. Okay, and then -1, 1, you can imagine something similar happens. This is going to end up at -4, 1. Multiply by -1, you end up at 4, 1. And then the y coordinate is going to be the same as it was in the previous case, 4, 2. No, 4, 4, 1. I apologize, 4, 1. 1, 2, 3, 4, 1, right there. So there you go. That's what that absolute value function looks like, more or less. Okay, there's more than one way to do this. Okay, so you can use a different method if you like, but this is how I'm going to do it in this section. Okay, part B. We have this crazy exponential function. Oh man, that's crazy. But its parent function, g of x, is 2 to the x. So a couple things. First of all, this thing has a horizontal asymptote at y equals 0 usually. But I'm going to multiply that by 3. Well, I still get a horizontal asymptote at 0. And then I'm going to subtract 5, right? So really this is going to end up at -5, right? My horizontal asymptote is going to end up at -5. Now as for the points on the graph, 2 to the x usually goes through 0, 1. Well, 2 to the x always goes through 0, 1, right? But we're interested in what this nasty thing goes through. 2 to the x goes through 1, 2. and then 2 to the x goes through negative 1, 1/2. Let's see where those 3 points end up under our transformations. So first of all, so I'm gonna subtract 1 from my x coordinates. Then I'm going to divide by a negative 1/2. Dividing by negative 1/2 is the same as multiplying by negative 2. So I'm going to divide by negative 1/2, but it's really the same thing as multiplying by negative 2. So that's going to give me 2, 1. And then for the y coordinate, I'm going to multiply by 3 and then subtract 5. So I'm going to multiply by 3. And then I'm going to subtract 5. So we end up at 2, negative 2. Right, 2, negative 2. Okay, same thing for the other points. So I'm going to subtract 1 from the x coordinate, multiply by negative 2, multiply a y coordinate by 3, and then subtract 5. So 0, 1. Here I'm going to subtract 1 from the x coordinate, multiply by negative 2. For the y coordinate, I'm going to multiply by 3, and then I'm going to subtract 5. 3/2 is 1 1/2. So 1 1/2 minus 5 is going to be negative 3 1/2, right? Okay, so I have 1, 2, 3, 4. 1, 2, 3 1/2 right there. Okay, and then remember our horizontal asymptote is at y equals negative 5. 1, 2, 3, 4, 5. So we have a horizontal asymptote right here. And so you get a pretty good idea of what the function looks like, right? So it's going to go kind of like this. You may be thinking to yourself, well, this is not what exponential functions usually look like. And of course you'd be right. But what's happening is that we've reflected across the y-axis because of this negative sign. So instead of going up this way, right, it's been flipped over, and so now it's going up that way. Okay, so that's what that one looks like. Okay, one more. This same sort of thing works for trig functions, right? So, I think we get into this bad habit of treating the trig functions completely differently from every other kind of function, but they don't behave any differently than any other kind of function. They work the same way. So if I want to graph tangent, I can do the same thing as I did before, right? So the parent function here, g of x, is just tangent x. And there were a couple of points that we talked about graphing when we looked at the trig functions way back in chapter 3. We said for the tangent function, we want to start at negative pi over 2 undefined, because it's really an asymptote, right? Then we said we wanted to do negative pi over 4, negative 1. That's on the graph of tangent. 0, 0 is on the graph of tangent. Pi over 4, positive 1 is on the graph of tangent. And then pi over 2 undefined, right? This other asymptote. So we're going to apply transformations to this just like we would to any other kind of function. So I'm going to add pi over 6 to the x coordinates. Pi over 2 is 3 pi over 6, so negative 3 pi over 6 plus pi over 6 is negative 2 pi over 6. That's just negative pi over 3. And then as far as the y-coordinate is concerned, I'm going to multiply with 2 and then subtract 1, but it's still just going to be an undefined value. I'm just going to write it down just for the sake of completeness. So this is 2y, still going to be undefined. And then y minus 1 is still going to be undefined. So we have an asymptote, it looks like at negative pi over 3. Negative pi over 4, negative 1. So if I add pi over 6, oh goodness, negative pi over 4 plus pi over 6. I'm going to use my calculator. That's negative pi over 12. Then I'm going to multiply the y-coordinate by 2. And then I'm going to subtract 1. So the point negative pi over 12, 3 is on the graph of f of x. 0, 0. I add pi over 6. Multiply by 2. And then subtract 1. Okay, pi over 4, 1. So pi over 4 plus pi over 6 is 5 pi over 12. 1 times 2 is 2. And 2 minus 1 is 1. And then finally, for my last asymptote, I'm going to add pi over 6. So that's 2 pi over 3. So I have an asymptote at 2 pi over 3. Okay. So let's graph this then, right? So these are the points that we want to plot. Negative pi over 3, negative pi over 12, pi over 6, 5 pi over 12. So I think I'll mark out pi over 12, right? Increments of pi over 12. So there's negative pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, which is the same as negative pi over 3, right? And then on this side, I've got positive pi over 12, 2 pi over 12, which is the same as pi over 6, 3 pi over 12, 4 pi over 12, 5 pi over 12. And then how far do I need to go? I need to go to 8 pi over 12, so it's 5, 6, 7, 8 pi over 12. So I've marked out these pi over 12s, right? But I know that I have an asymptote here at negative 4 pi over 12, or in other words, negative pi over 3. I know that at negative pi over 12, I'm at negative 3. At pi over 6, I'm at negative 1. So here's pi over 12, pi over 6, negative 1. And then 5 pi over 12, 1. 1, 2, 3, 4, 5. Pi over 12, 1. And then 6, 7, 8 pi over 12, I've got another asymptote. Okay, so there you go. And of course this thing repeats, right? It repeats over and over again, so we've got another copy, you know, like going this way, and another copy down here, right? It's going to go on and on forever, but as long as you get one period, I'll be happy. Okay, so that's what that one looks like. You should label your axes. It's going to clutter the picture too much for me to label every single one of these, but maybe I'll just label the ones that we actually found points for. So this is 5 pi over 12. And then this is 2 pi over 3 out here. Right? So that's what that graph looks like. Okay, so this is how really complicated transformations work. Okay, so you can do it. You just have to be a little bit more careful, I think, than the way that we've been doing it in the past when we had kind of simpler transformations to work on. One last thing that I want to say is that we could also apply nonlinear transformations to functions. It's a lot more difficult to do this, but it's useful to kind of think things through a little bit. Like we could compose f of x equals sine x with g of x equals 1 over x to obtain h of x equals sine of 1 over x. Now what would this thing look like? Well, remember that sine alternates between -1 and +1. As x gets larger and larger, 1 over x gets smaller and smaller, so it gets closer and closer and closer to 0. Which sort of leads me to believe that sine x is I think as x gets really large, sine x is gonna, or sine 1 over x is probably gonna get close to 0, closer and closer to 0. As x gets really small, as x gets really, really close to 0, though, this is really interesting. As x gets really close to 0, this number is going to get bigger and bigger and bigger. You're going to see this thing alternate a bunch the closer x gets to 0. Let's look at it in Desmos. Okay, so we want to do sine of 1 over x. Yeah, so as x gets really large, this thing is just going to go to 0 in either direction. But as x gets close to 0, look at how much you're alternating. You can zoom in all day, but you're going to see like this just alternates and alternates and alternates. Faster and faster the closer and closer you get to 0. It's really fascinating. You're going to look at this function a lot in calculus, I have a feeling. Anyway, but the point is, we could do compositions that are nonlinear, right? So we could do nonlinear transformations. It's kind of hard to do, but it's useful to kind of think through it. But anyway, one type of nonlinear transformation is very easy to work with, and it's the absolute value. So just recall, the absolute value makes everything positive, right? So if h of x equals absolute value of x is the outer function of a transformation, then we can graph g by just graphing f, but just reflecting everything above the x-axis. Let me show you what I mean. So here we have the graph of f of x, right? And let's say that we wanted to graph g of x equals absolute value of x. What that's going to do to the graph is it's going to look exactly like the parent function, but whenever it dips below the x-axis, it's going to be reflected, right? So like right here, it's going to be exactly identical to f of x, but suddenly where it dips below the x-axis, it's going to kind of spring up and look like its mirror image, kind of like this, okay? And then at this point, it follows the original function again, like that. Over here, it's going to bounce back up, right? It's not going to dip below the x-axis, it's going to bounce back up, kind of like this. So that's what absolute value of g of x, or sorry, that's what absolute value of f of x would look like. You know, it has all of these bounces in it. So let's practice some more. Let's graph f of x equals absolute value of x cubed. So first of all, x cubed goes through 0, 0, 1, 1, 2, 8, or 1, 1, 2, 8. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, negative 1, negative 2, negative 8. 1, 2, 3, 4, 5, 6, 7, 8. 8. Okay, so this is what x cubed looks like, but we want to graph absolute value of x cubed. That means that, you know, here it's going to look identical, right? No problem. But here, on this side, it's going to bounce back up. So it's going to look like that and like that. So it's going to bounce back up this way. Okay? So you would get this thing that ends up kind of looking like a parabola, but it's a cubic. It's the absolute value of a cubic. Let's do another one. So here we've got f of x equals absolute value of x minus 2 squared minus 4. This transformation is pretty easy to apply, right? We're just shifting right 2 down 4, right 2 down 4, and 1, 2, 3, 4, there and there. We go 5, 6, 7, 8, 9, there, there, and I think that's good enough. Okay, so this is what the function would look like without the absolute values around it. But with the absolute values, then it's going to look like this. But when we get to this point, it's going to bounce back up. Instead of going down to -4, it's going to go up to +4. Or like this. So it's going to look like that, kind of like a little W. Okay, so this is what absolute values do to functions as far as transformations are concerned. Oh, let's look at this crazy absolute value inception. Now, you could graph this by using the piecewise definition of absolute values, right, to figure out what's going on. But I'm just going to graph this function, right? So this is an absolute value function shifted left 1, down 3. Left 1, down 3. So it's going to look like this. Right? So this is what the function would look like without the absolute values around it. But because of the absolute values, it's going to have to look like this instead. So when we reach this point, we're going to bounce back up. And we're going to come up to 1, 2, 3. So it's going to go like this. This one looks even more like a W than the previous one, right? That's what that one's going to look like, okay? So that's how you deal with absolute values when you're transforming functions. And that's all I have to say about transformations, right? So these are much more complicated transformations than what we've done so far in the course, but you're well equipped to handle any kind of linear transformation now. So that's all I have to say about that. See you in the next section.